I'm waiting for the students to be joined. Hi, Tashri. Good evening. How are you? So, hi, Pooja. How are you? Good evening. So, how's your Diwali? Is it good? Was it good? Okay. So now let's get back to study now. Okay. So on the next lecture, please be on time. Got it? I know there is a long holiday break that you have got. and after that some laziness came into the mind and body. Okay, but you should have you all of you have to recover it very soon because exam is ahead. Okay, so tomorrow onwards, please be on time. Got it? Now, we are studying the semiconductor. In that, we are on the topic of intrinsic semiconductor and extrinsic semiconductor. Okay. Now, the what is intrinsic semiconductor? I have already discussed it, but it is just for your revision. Okay. So, an intrinsic semiconductor is made up of the pure element or pure compound. Those semiconductor was found naturally on earth crust or earth surface, that only that we are called the intrinsic semiconductor. Okay, so for example, these are the silicon and germanium basically that we have. These are the tetravalent compound, tetravalent element you must say, which means they have a valency of 4. Got it? So these silicon and germanium are tetravalent also. The screen is visible to you, no? And my voice is audible. So the naturally found semiconductor on Earth. Okay, got it. So naturally find semiconductor on Earth are silicon and germanium basically. Okay, these are the simple element because it only consists of one element like silicon and germanium. Other than that, we also get some compound which are like cadmium sulfide or anthracene. These are also be termed as the semiconductor, but they are not pure made up of pure element. They are the pure compounds. Okay. But what do we have the problem with intrinsic semiconductor? These are not very conductive at room temperatures. Okay. All our devices work slightly above the room temperature, but basically we want such a device or such a semiconductor that could be run on a feasible basis on the room temperatures. Okay. To run the semiconductor, we need the conduction to be happen in them. But these semiconductor like silicon and germanium will not show any significant conductivity on room temperature. When we put that those materials on room conductor and check their conductivity, so that could be very low. That came out to be very low. So that is why is happening, because at room temperature there is no significant thermal agitation takes place. Thermal agitation is nothing but the external energy we are providing for the valence electron to jump into the conduction band. Got it? So for that, what we will do, so why is what is the reason for that? The low conductivity. So we do not have sufficient conduction electron on the conduction band. Okay. So that is the main reason, which means we have very few charge carriers which can carry the charge. Okay. So very few charge carriers are available in intrinsic semiconductor. That is why the conductivity of intrinsic semiconductor at room temperatures are very low. Got it? So there will be no use of it, because if the conductivity is not so high, then we cannot make a device which uses this semiconductor, because there is no conductivity at room temperature, or the conductivity we are having is very low. So that is why no device can be made up of that, these materials. So we have to find the ways to uh, conquer this issue. Okay. Now, If we move on to the next slide, the intrinsic semiconductor are the four valence I have told you, silicon and germanium also. There are four valence electron with four nearby atoms. Okay. You can see in this is the nucleus, and these are the four electrons. Okay. This blue part is the nucleus, and these are the electrons. Now, these atoms are bounded like that. The bond between them is covalent bond, which means these electron is not transferred from one atom to another. These electrons are being shared. Okay, because covalent bond means sharing of electron. Ionic bond means transfer of electron. Okay. Now these are the bonds exist between these individual atoms. Okay. So one atom is surrounded by its four atoms and making a single covalent bond with other four atoms. Okay. Now this is the crystal structure or lattice structure, you can say, of the tetravalent compound. Now this crystal material is formed by the covalent bonding of each atom with its four nearest neighbors. Okay. So this is happening because of this covalent bond has been formed between any of two atoms of silicon or germanium. Okay. Now these are gallium atom. So we have these four valence electron in the outer shell. These are the four electrons. Now each one of them make a bond, single bond. You can see here. So this you can say also, this is the structure. This is the structure of silicon. Oh, sorry, germanium. Okay. So you can see here in the conduction band, there is no single conduction electron because this is the semiconductor. So at normal condition, there will be no electron in conduction band. So what do we have to do? We have to just ignite them, or we have to provide some external energy so that the electron of valence band get excited, absorb that energy and jump into the conduction band so that we can conduct the electricity. Okay. And then semiconductor will behave as the conductor only. So what will happen when we provide heat energy to them? Just look at the slides. We provide heat energy to that. One electron breaks its bond because of the heat energy provided by us. This electron become free. This electron become free. As you can see here, this electron from valence band jump right into the conduction band after having the heat energy. Okay. Now again the another electron goes up and this process would takes place. Okay. But one thing happen here, and what is that? These electron which is making itself free left with a hole, and hole is nothing but unfilled energy levels. Okay. So these holes are nothing but these holes are nothing but unfilled unfilled energy level. Okay. So what happens then? The electron surrounded by these, the electron participating in covalent bonding jump into that vacancy, which means this hole, look at this, look at this electron, which is going here to fill this vacancy. And here the vacancy is created, which means not only the electron is moving, this hole is also moving. So hole is also moving. Got it? Then you can see here this conduction band electron will fill this vacancy. Now these are the valence electron which is bounded in the covalent bond. This is the covalent bond you will see. These are the covalent bonds. And these are the broken covalent bond showed by dotted lines. Okay. And these are the free electrons. These are the free electron which is responsible for the conduction in semiconductor. Okay. And these are holes. Now, intrinsic semiconductor में the number of thermally generated electron is always equals to the holes. Number of holes has been created because one electron leave the bond, so one hole has been created, which means as many of number of electrons break the bonds, same amount of hole will be created. Got it? So the concentration of free electron is equals to the concentration of hole, which means number of electron per unit volume is equals to the number of holes created per unit volume for intrinsic semiconductor. So any here is the concentration of electron, which is the number of electrons per unit volume. And these are also called the number density, you can say. Okay? Because here we are taking numbers as one of the quantity. The number of electrons per unit volume. Now NP is the concentration of holes. Okay. So for that, NP is equals to Ne is equals to NP, which means number of holes has been created is equals to the number of electrons, free electron you will see. Okay. And this is equals to Ni, and Ni is nothing but intrinsic charge concentration, or you can say it intrinsic carrier concentration. Whatever you can remember easily, you can pick up that. So this Ni is also called as intrinsic concentration. Simply you can say it intrinsic concentration, or intrinsic charge concentration, or intrinsic carrier concentration. Okay. Whichever feels you better, you can keep the remembering it. Okay. Now if we apply external source to this semiconductor, which is already in conduction mode, okay, which is already in conduction mode. So if we connect it by a battery of electric potential E, then what will happen? All the free electrons will move towards the positive plate, because this plate is positive and this plate is negative because it is connecting to the negative terminal. So what will happen? These all electrons run towards the positive plate, and this all holes, basically these holes are not moving anywhere, only the electrons are moving. But what will happen? This electron will jump to this vacancy, so that this hole will come here. Then again this electron will jump to this vacancy, because this is also repulsive force, na? Here is also negative charge, and negative charge repels negative charge. An electron carries a negative charge. So these electrons are repel. They can fill this energy level. So here the hole is moving in that way, again in this way. So we will see that it will appear that the hole is also moving towards the negative plate. Okay. So these electron move towards the positive plate. Again, the vacancy filled by these electrons, so that it will appear the hole is also moving towards the negative plate, as you can see in the emanation. So the current which will flow in an intrinsic semiconductor consists of both electron and hole current, because electron is also moving, which contributes a current. When electron moves, current will flow in the opposite direction to the flow of electrons. Okay. And the hole is also moving, which is considered to be a positive charge. So current will be in the direction of positive charge. So there are two currents in the semiconductor, which is current produced by electrons and current produced by hole. Okay. So this consists of the total current in the semiconductor. This current I is provided by this battery. So we can say that this current I is equals to IE plus IH. Got it? Now tell me one thing I want to ask you guys, that why we have taken the direction of current opposite to the electron. We all know that this current is only running because of the electrons. Then why we will take the direction of current in the direction of positive charge? As we all know that positive charge cannot move. Positive charge is there and there. Okay. Protons are there in the nucleus. Only the electron is moving. Then why we have assigned this direction of current to be a positive charge direction? Any one of you knows the answer? Write it in the comment box. Huh? Okay. At any point of time, you can write it. Now, at room temperature, conductivity of intrinsic semiconductor is very low. We have discussed it. So therefore, no important electronic device can be constructed or can be developed by using these semiconductor. So what we have to do? We have to invent something more, something extra we have to do. Okay. So these are the questions. Firstly, you will attempt it. A hole in an intrinsic semiconductor is. So what is the hole in the intrinsic semiconductor? Is it an antiparticle of electron? A vacancy created when electron leaves a covalent bond? Absence of free electrons? Or an artificially created particle? Now write this answer. A, B, C, D are the options. Now comment the answer in the chat box. I'm waiting for your response. Then we will move further in the lecture. Tashri is here. Every one of you guys, please answer it. Na? Pratibha is there. Samsung, Pooja. All of you answer it. What is the correct option of this question? And be responsive, guys. It's for you. The more you respond, the more you will get. Okay. So a hole is nothing but the vacancy created when an electron leaves a covalent bond. So whenever the electron leaves the covalent bond, there is a vacancy created. I have seen it. We all have seen it, how it is possible. So option B is the correct option. Okay. Now, extrinsic semiconductor that we are interested in. Extrinsic semiconductor is nothing but the solution of that problem that we are facing when we are using intrinsic semiconductor. When we use intrinsic semiconductor at room temperature, so there is no suitable thermal, sorry, not suitable conductivity we were getting. Okay. So there is no scope of using that kind of semiconductor in any electronics devices. Got it? So we will come up with a solution in the form of extrinsic semiconductor. Now basically one idea that you will all get कि ये it will resolve the problem that we are having previously, which means it makes the semiconductor more conductive at room temperature. But how? How is the question that we have to answer? Okay, so let's just find the answer of that question. So this extrinsic semiconductor is to use for improving conductivity of intrinsic semiconductor. How? So this process of improving the conductivity of an intrinsic semiconductor is termed as doping. And what is doping? We will look after it. So doping is the process of deliberately adding some foreign impurities or atom in a very small amount to the parent atom, the actual atom of semiconductor. Okay. Now, if this is the silicon that I have, okay, and we have four bond here, four electrons. Okay. So what we will do, we will add some atom, let's say A, to this crystal structure of this silicon so that it become more conductive, more conductive. If you are the engineers that time and you were facing that issue, what should come first come in your mind? The problem is the conductivity, less conductivity, and you have to make it more conductive. Okay, more conductive means providing the same energy at room temperature. We want more electron in conduction band. Okay, so as engineer or physicist or scientist, your role is to increase that number of electron in conduction band. How is that possible? So the idea came here is to add that kind of atom which is similar to silicon or germanium in size, so that the number of electrons at the same energy that foreign atom will also produce and the silicon is also producing. So it will just double the number of electron in conduction band, and that is sufficient for us. Okay, got it? The idea of doping is to deliberately adding some foreign impurities or foreign atom. I am saying this foreign because it is not a part of silicon itself. Okay, we will say it the impurities. So we will add some impurities to this pure atom of silicon or pure crystal lattice of silicon or germanium, and it will increase the conductivity of that semiconductor by increasing the number of electrons or number of holes. Got it? Now, so these impurities are nothing but these impurities are called dopant. What is this called? These are called dopants. So one thing you can do, either you can increase the number of electrons or you can increase the number of holes. Now, in that intrinsic semiconductor in which number of electrons are more than the number of holes, which means negative charge carrier are dominating there. So that we will call it as n-type semiconductor, which means majority of the charge carrier there are n, means negative. Negative means electrons. So in n-type semiconductor, majority charge carriers are electrons. In opposite to that, for p-type semiconductor, we have two types of semiconductor we will have in intrinsic semiconductor. And in extrinsic semiconductor, it is p and n type. Okay. N type I have already told you. P type, which means positive. P means positive. So where the dominating charge carrier are positive charge carriers. But where the positive charge is nothing but the number of holes has been created. Okay, got it? For, let's say, for if you want to increase the number of electrons, okay, like for silicon, you want to increase the number of electrons. So you must add an impurity such that which has extra electron. Okay, so that could be a pentavalent impurity, because you cannot increase this size so much. Why? Because if you take a bigger atom, this is the silicon atom, let's say, and if you take the bigger atom, the impurity, so it will distort the shape. It will distort the shape of crystal lattice, shape of crystal of silicon. So that is not we want. We do not want to distort the shape of it, because then it will acquire some other properties also. That we will not wish to do. What we want to do, we just want to increase the conductivity of that atom. Okay. So to avoid this distortion, we need the atom which is similar to in the size of silicon. If silicon is of this size, this atom must be of this size. Okay. Or that could be only possible because the silicon has 4 valence electron. So that impurity must lie in the range of 3 to 5. Okay, exactly 4 if you will take, it will like it gives nothing to us, because 4 are the outer shell, outer electrons, valence electron, then 4 will be covalented. Now the same situation is there. Okay, so there is no free electron. Only the way to free the electron just to use one extra electron. Okay, we can use 5 pentavalent impurity, or we can use the trivalent impurities. Okay, now all of you will answer to that. If we use a pentavalent impurity which has five electrons in the outermost shell, or we can say in the valence shell, in the valence shell we have 5 electron, and all these atoms are having 4 electrons in their valence shell. So what we can do, if we are using this pentavalent impurity, this is the pentavalent impurity, if we are using that, which has one extra electron, because 4 electron will be bonded here with this silicon. So 5 minus 4, we will have one extra electron, which is the conducting electron. Okay, got it? Which means the semiconductor in which we doped a pentavalent impurity will act as the negative charge carrier, because there the number of electron is excess in amount. So that extrinsic semiconductor will act as the n-type semiconductor. Got it? And similar reason for the 3 electron trivalent it has one less electron, so we have one extra hole there. So that is means the positive charge carrier will dominate in that case. Let's just understand it one by one. Okay. I hope you got the idea. Okay. If you have any kind of doubt, you can ask immediately. Okay. Now, due to doping, the conductivity of semiconductor increased manifold, which means many times increases. Okay. So these are called the extrinsic semiconductor, the semiconductor with impurity. Got it? Now, how to select the dopant? Dopant is nothing but the impurity. It is impurity. So the dopant first condition I have already discussed it. The dopant has to be such that it does not distort the original pure semiconductor lattice. Okay, got it? So we cannot use a much bigger atom to that and a much lower atom also. Okay. So the next point is it occupies only a very few of the original semiconductor atom site in the crystal, which means we only add a few electron or few atoms of impurity to the original semiconductor. ओके, ऐसा नहीं है कि भर भर के डाल दिए उसे, थोड़ा बहुत थोड़ा, वेरी फ्यू. The third is the important one. The necessary condition to attain this, that is the size of the dopant and the semiconductor atom should be nearly the same. Okay. Think in terms of the outer valence electron. The semiconductor, original semiconductor has 4 valence electron in the outer shell. Okay. So we must choose that atom which has 5 electron in the valence shell or 3 atom, 3 to 5, because these are the nearest one to 4. Got it? So we have two types of dopant then on the basis of that. First is the pentavalent, जिसकी वैलेंसी होगी 5. ठीक है, and it is arsenic, antimony and phosphorus. Okay, etc. But these are the important one. Okay, so we have tetravalent semiconductor, SiNge. For that we will use this pentavalent impurity. Example for that is arsenic, antimony and phosphorus. They have 5 electron in the outer shell or the valence shell. Okay. This type of semiconductor is known as N-type semiconductor. And why is so? Because this is the impurity, because it has 5 electron in the valence shell. Okay. So when silicon come into the contact of it, silicon has only 4 electron. 4 electron will bond with each other. Okay. This will like this, and this is also will like this. Okay. Only the 1 electron has left free. So here the number of electrons, free electrons, are much higher than the number of holes. So that is why here the majority charge carrier is, the majority charge carrier is electron. Okay. That is why it is called the N-type semiconductor. N means negative. Remember this. Huh? And who is negative? Electron is negative. Now, the other is the trivalent. Trivalent means tri means 3. So the valency of the atom is 3. So it is indium, boron, and aluminum. Okay. These impurities, when added to the semiconductor, intrinsic semiconductor, so they will form an extrinsic semiconductor, which is known as p-type semiconductor. Why p? P means positive. So here the majority charge carrier here is the majority charge carrier equals to whole. Okay. So these are the majority charge carrier. So in n-type semiconductor, we will learn it how it is happening. So when Si and G is doped with a pentavalent impurity, these are the group fifth element, okay, in periodic table. So n-type semiconductor is formed. Now when germanium is doped with arsenic, these are the germanium atoms having four electron in the valence shell. Okay. Now these are doped with this arsenic, which is the pentavalent atom, which means it has 5 electrons. You can count it as 1, 2, 3, 4, 5. So it has 5 electrons in the outermost shell, in the valence shell. Okay. Now what will happen? All these electrons will bound it together, the four of it, arsenic, four of the germanium. So four electrons of arsenic will bound with covalent bond with the germanium atom. No problem in that. But arsenic has 5 electrons. Four has been bonded. So how many electron has been left? It is 1 electron. You can see here. So this electron is acting as the free electron. Okay. And right now we do not have provide any kind of heat energy to it. You can say it. So there is no valency created by that atom which are bonded together of germanium. Okay. It is just happened when we dope this impurity. Got it? Now, providing the heat energy to it, these electrons will come out for germanium. So you can see for two holes, number 1 and number 2, there are 1, 2, 3 electrons. So for every two holes, there will be 3 and more electrons come out to be there. Okay. You can see it here. These are the valence bond. This is the donor level. Okay. 0.045. So this electron is already present here. The free electrons, when you provide some energy, thermal energy, it will directly jump into the conduction band because it is very near to the level energy of conduction band. Okay. And then the process that we have studied so far. Okay. Now, the carrier concentration in n-type semiconductor, which means who are the responsible one for the conduction of electricity in n-type semiconductor. We have to find out that. So when intrinsic semiconductor is doped with donor impurities, and who is the donor here? Donor is electron. Okay. Donor impurity is arsenic, but arsenic has donated what? Arsenic has donated electron. Got it? So when donor donate the electron, that semiconductor form is n-type semiconductor, negative. So for that, the number of free electrons will increase as we have seen it. Okay. Number of holes will decrease. Now, how is this happening? Because it can be possible that the free electron donated by this impurity will also fill one of the gap, one of the energy levels gap created by breaking the covalent bond, which means there is lesser number of holes than the electrons. Okay. So number of holes decrease because a large number of electrons present increase the rate of recombination of the electron with holes, as I have already told you. Okay. When arsenic combined with this germanium atom, number of electrons will increase because it has already a free electron. Okay. So when the bond breaks, vacancy created, that electron will immediately fill that vacancy because it is free to move. So the rate of recombination of electron and holes will increase. Okay. So that is why the number density of these holes has been lesser in comparison with electrons. Got it? Now, so in n-type semiconductor, free electrons are the majority charge carrier. As I already told you. So the free electrons are the majority charge carrier in n-type semiconductor. Okay, and the holes are the minority charge carrier. ऐसा नहीं होगा. It is not like that कि holes will not contribute into the conductivity. They will contribute, but they are the minor level. They are the minors level. So these are the minority charge carrier. The majority charge carrier is the electrons in n-type semiconductor. Okay. So you can say it that number density of electron is very, very greater than the number density of holes. Okay. So if Ne and NH represent the electron hole concentration, then you can learn this formula. This Ne dot NH is equals to Ni whole square. Ni whole square means when Ni is the intrinsic carrier concentration. Okay. So you can learn this relation. So you can see it when the concentration of electron is increased above the intrinsic value by the addition of donor impurities, the concentration of hole will fall because it intrinsic value. Okay. You can see here this Ne dot NH is equals to Ni square. Ni is a fixed value. It is a constant term. So if Ne will increase, so that NH should be decreased. Okay. To maintain this fixed value. Got it? That is what it is written in this statement. I hope you are clear with this n-type semiconductor. If you have any kind of doubt, you can write into the chat box. No? Okay? And please use this chat box. It is for you. Now, what are the p-type semiconductor? When the dopant has been changed. Now, in the previous one, what kind of dopant we are using? We are using a pentavalent dopant, which has one excess electron. Now, this p-type semiconductor, in which majority charge carrier are the holes, positive charge carriers. So in that, what we will see, these in p-type semiconductor, the dopants that we will use are the trivalent impurities, okay, which has a lesser value of electron. Okay. You can see when silicon and germanium is doped with a trivalent impurity, these are the group third elements. You can remember this information. Okay. Group third elements behaves as the trivalent impurity, such as indium, boron, and gallium. So this p-type semiconductor is be formed. Okay. Now, when germanium is doped with indium, okay, this is the germanium having 4 valence electron in the outer shell. Do not think इसके ऊपर वाले में चार्ज नहीं दिखाएगी. These are the or electron. These are not showing because there are atoms above of it. ठीक है. Now this indium is here. So what will happen that this three electrons will make the covalent bond of it. Will make a covalent bond. So what will happen? A vacancy has been created. This is the incomplete bond, you can say. This already is a vacancy. Okay. When you provide some energy, this vacancy will be filled by the electron. So you can see here in that intrinsic case, the number of electron will be equals to the number of holes, because as many of the number of electron will came out, same amount of holes will be created. But here already one hole is present. One hole is already present. This. So you can see for one electron there are two holes. Okay? And this will happen on a very large amount. So the number of holes you will have are the greater. Okay? These are the acceptor level. Okay? Acceptor. This is also called the acceptor impurity, you can say, because it accepts the electron. And the previous one are the donor, which can donate the electron. Okay? So you can see the energy levels of that. This electron will come on the conduction band again. Okay? So in p-type semiconductor, holes are the majority charge carrier and the electrons are the minority charge carrier, because the majority charge carrier here is the holes. Okay? So the same relation is there. Number of holes per unit volume is very, very greater than number of electrons, because of that acceptor impurity, which can accept the electron, and it has already a vacancy. So we dropped in the ppm. Ppm is parts per million. ppm you will receive a term. It is parts per million. Okay. So for per million of germanium or silicon atom, we added these impurities. Okay. Where Ne and NH are the electron and hole concentration in n-type semiconductor. Okay. So for this is not n-type, this is p-type. Okay. So Ne dot NH is equals to Ni whole square. This is the relation where Ni is the intrinsic carrier concentration, Ne is the electron concentration, and NH is the whole concentration. Okay. Now you can answer this question. The impurity atom with which pure silicon should be doped to make a p-type semiconductor are those. Answer this. Phosphorus, you will see it's a pentavalent. Carbon has outer valency of 4 electron. So this cannot be the answer. Yeah, arsenic and antimony we can do something. Okay. But we have to make it a p-type semiconductor. This phosphorus and antimony both have 5 electron. Only this boron has 3 valence electron. So this can act, this can create a vacancy, this can create a vacant space. So it can increase the number of holes. So the p-type semiconductor will be there because it is the acceptor type of impurity. So option B is the correct option. Okay. So thank you so much guys for being attentive in the lecture. Okay. I hope you are clear with all the concept that I have taught you. If you have any kind of doubt, you can write it in the chat box. Otherwise, the lecture is over. Thank you so much, guys. Thank you so much for having me. Take care. Bye bye. Okay.